Hi, this is Professor Pradyot from Leadib Academy. So we are discussing IBDP Chemistry HL Paper 2 of May 2019. The paper reference has been already indicated, okay? And we are looking into the video solutions, okay? So interestingly, while understanding and discussing the video solutions, we are also understanding the underlying concepts, okay? So it is not just the plain vanilla solutions, but we are discussing the underlying concepts. So that is very extremely will be useful to revise some of the concepts, okay, which you might have forgotten or probably have not understood. So it will be a good revision kind of, okay? And anyway, if you are interested in understanding the detailed concepts, okay, please do subscribe to our courses, because we at Leadib have uploaded the courses for chemistry, physics, maths. So please do visit our website, Leadib Academy, okay? Anyways, so now start looking into the question number 6. Phenyl-ethene can be polymerized to form polyphenyl-ethene, that is a polystyrene, okay? So let's try, okay? And they are asking, draw the repeating unit of polyphenyl-ethene. So in short, they are asking us to find out the monomer, okay? Repeating unit means monomer, okay? And this is basically a polymer, simple. So monomers, when they get combined, we get polymer. So how to look into this? Okay, very simple. So let's redraw this structure. Okay, so they are indicating like this. So C H. Okay, let me show slightly differently so that it would be helpful. C H double bond C H and H. Okay, now please understand that when this is the monomer, okay, this is how the compound is, but when it gets polymerized, what is going to happen? Okay, understand the logic that this one of the double bond, that means the pi bond is going to open. Okay, you can think of like this, that it is getting opened up, and we will get a structure like this. C H C H H, and now we need to show that this double bond which had disappeared is appearing here. Okay, so instead of this we get this. Okay, and these are called, the orange one are called continuation bonds. Okay, why? Because there will be another molecule which will be similar looking, okay, identical, and it will get connected to that. Okay, so just to show, just to make it very clear that what we are referring to is like this. There is going to be another molecule, another monomer which will be similar one, C H, and it will get combined. Okay, you can now see very clearly C H H, and again it will get combined. Okay, it will continue the process. So what I mean to say, it is like this. Okay? So it can get combined and you will get a chain, okay, a very, very massive chain, one after the other. So this is called a repeating unit. So very, very careful. You need to be very careful to show the continuation bonds. Okay, that is very, very important. Hope this is quite clear. Okay, and interesting. Okay, so let's look into the question number 6b. Phenylethene is manufactured from benzene and ethene in a two-stage process. The overall reaction can be represented as follows with delta G naught, that is the Gibbs free energy, is equal to plus 10 kilojoules per mole, okay, at 298 Kelvin. So first of all, just for our information, what does it mean? Delta G naught is plus, that means it is non-spontaneous, okay? It is not going to happen by its own. That means we need to either supply a catalyst or increase the temperature, okay, to make it spontaneous. So let's understand now what's the question. So they're asking calculate the equilibrium constant for the overall conversion at 298 using section 1. That means section 1 means formula, okay, simple one. So let's try and get it. I'll get it for you from the section 1. So it shows delta G naught is equal to minus RT ln K. So at equilibrium, okay, at equilibrium, this is the reaction. Okay, this is the equation. Gibbs free energy is equal to minus R. R is nothing but a gas constant. T is the temperature in Kelvin. Okay, and K is the equilibrium constant for the given reaction. Okay, simple. So with this, they are asking us to calculate the equilibrium constant. So let's say from this, ln K is equal to minus delta G naught upon RT. Okay, very, very simple. Now let's start putting it. Delta G naught is how much? It is given as 10 kilojoules. We need to be careful that converted into the joules, SI units. Okay, then comes the R. So we know it, 8.31 joules per mole per Kelvin. And then temperature, that is 298 Kelvin. So by doing this, what we will get, okay, it will be simple. By doing this calculation, we should be getting minus 4.04 ln K. Please remember it is ln K. So how much would be K? Put it in the calculator. K will work out to be 0.0176. Okay, this is the equilibrium constant. Simple, just the formula application. Okay, pick up the formula so you don't need to remember it. Okay, just put it. Okay, only care need to be taken while converting. Okay, proper units. 10 kilojoules converted into 10,000 joules. Picking up the value of R properly and temperature obviously in Kelvin. Simple. Question number 6C. Another interesting question from organic. The benzene ring of phenylethene reacts with nitronium ion, NO2 plus, and a C double bond C, okay, reacts with hydrogen bromide. Compare and contrast these two reactions in terms of their reaction mechanism. So let's try to analyze this. Okay, let me try to show. Okay, first HBr hydrogen bromide, and then nitronium ion. So let's show nitronium ion. So first, understand, is there any similarity and what is that? Okay, so first of all, hydrogen bromide, bromine is more electronegative. Okay, so it is going to draw the electron from the hydrogen, making it polar. Okay, and bromine is this. While in case of this nitronium ion, already it is plus. And now probably you people have already got the hint that what we are talking about. So these are nothing but both are electrophiles. Okay, both are electrophiles. What is mean by electrophiles? That means they are deficient in electrons and they are looking for something which basically the rich in electron. They are looking for, both are electrophile, both means H delta plus as well as N plus. Okay, that means as a this compound, okay, so H plus is going to attack, okay, this double bond, okay, because there is a rich source. Why double bond? Because this is a loose pi electrons, so it is basically going to attack here on this double bond, while N plus is going to attack, or NO2, okay, it is going to attack this benzene ring. So both are electrophilic attacks. Now in case of HBr, so that is the similarity. Now in case of HBr gets added, okay, added across the double bond. Okay, so that is basically addition reaction. While in case of NO2 plus nitronium ion, it substitution in benzene ring, because we know in benzene ring it is extremely stable, so we cannot add so easily. Okay, it can get substituted. Okay, and we cannot basically break the benzene ring. Okay, because that means we are going to lose the aromaticity, so that is very, very difficult. Okay, so that's the reason that in this case, so these are the differences. Okay, so the similarities are both are electrophilic attacks, but their reaction mechanism is going to be different. One, HBr is going through addition reactions, getting added across the double bond, okay, while NO2 plus will be getting substituted. Simple logic, okay, electrophilic substitution. Okay. Extremely, extremely simple. Okay, let's look into the question number 6D1. Interesting question. The major product of the reaction between hydrogen bromide and C6H5 CHBr CH3. Okay, it is, and the minor product is C6H5 CH2 CH2Br. Okay, so the question is, outline why the major product is so and so can exist in two forms and state the relationship between these forms. Okay, so the question first, that which are those two forms. Okay, so first of all we need to mention that which is the major product. Okay, so important part that this is going to be the major product. Okay, and this is the minor. Why it is so? The reason being, this is as per Markovnikov rule. Markovnikov addition. Okay, so why it is so? The simple, it is based on the stability of the carbocation. When there is a breakage of this double bond, okay, because this is getting added across this double bond. So when this double bond breaks, one there are we get one carbocation and another is a carbanion. So which one will be carbocation? That depends on the stability. So higher the stability, that product will be major product. So in this case, you must have identified that this carbon, okay, when there is a carbocation which is getting formed on this carbon, okay, that is going to be more stable because there is a supply of electron from this, basically the phenyl ring or benzene ring and this methyl group, okay, CH2. So that's the reason this carbocation is going to be more stable, and that's why the Br gets preferentially attached, okay, the preferentially get attached to this carbocation, and automatically hydrogen will get attached to this. Okay, hydrogen as per the Markovnikov addition always get added to the less substituted carbon. Okay, that's the rule. Okay, simple. So this is what we have seen. Okay, so these are the basically. Now let's look into that. What are the two forms? So understand now what is so special about this. Okay, what is the special about this carbon? So you will understand that this carbon is special simply because, okay, simply because on four hands it is having four different atoms or groups. So this is one, that means this phenyl ring. Okay, we are referring to this carbon, okay, which I put the square this one. Okay, so this one phenyl group, then there is a bromine second, then this carbon or we can say methyl group. Okay, overall it's better to consider as a methyl group, this complete one. Okay, so that is 3, and this hydrogen 4. So this means that this carbon has been attached to 4 different either atoms or groups. It means this carbon is a chiral carbon. Okay, chiral carbon, simple. And it simply means that chiral carbon means the carbon atom which is attached to 4 different groups, okay, or atoms. So in this case, this is a chiral carbon atom. While if you look into the second possibility, which is a minor, it is not. Why? Simple, because there are 2 hydrogen atoms which are identical atoms. So that means this is out. This is not the chiral carbon at all. What is the specialty of chiral carbon? Okay, simple. Okay, it means that it is going to give 2 enantiomers. Okay, this means it will have 2 possible enantiomers. That means it is going to be optically active. Okay, that is another characteristic that it is going to have. And there are 2 possible enantiomers. So what is the specialty? Okay, they are going to be, so these are this one, they are going to be non superimposable mirror images of each other. Okay, this is the key point. That means these two forms, these two, okay, because it's a chiral carbon, so it is going to exhibit the optical isomerism. That means it will have two possible enantiomers, and those enantiomers mean they are non-superimposable mirror images of each other. Okay, it is extremely simple. Okay, optically active while the minor one is out. Okay, so we'll not talk about that at all. Our focus would be only on the major product. There is a optically active carbon or chiral carbon. Okay, because of that there will be two possible enantiomers, that is non-superimposable mirror images. Okay, extremely simple. Okay. Okay, 6D2, the minor product C6H5, CH2, CH2Br can exist in different conformational isomers. Okay, conformational forms or conformational outline. What this means? Simple. What is mean by conformations? So just think of this part, okay, and understand that this carbon is basically tetrahedrally attached. That means there are two hydrogens and Br, and there can be a free rotation along this axis. Okay, just visualize that it is getting rotated. Okay, about this carbon and carbon bond. Let me show which one we are referring to. So think like this. So along this axis, there can be a free rotation. Okay. So because of this free rotation, so I'll say along C bond C, there can be free axial rotation. Think like that it is like a fan. Okay, it moves. Okay, think like that this bond what I have shown, there is like a shaft, and this part, okay, whatever I have encircled, that is rotating. So what is going to happen that right now this hydrogen, so let's say this is 1, this is 2, and this is 3. So after some time, maybe the Br will go up. Okay, this H1 may be at the H2 position and H2 will be like this. Okay, so you will keep on getting a different conformational isomers. So these are called the different one. Okay, whatever the different configuration are called conformational isomers. Okay, it's very simple. And in the previous one, in the major product, this is not possible because all are identical, all were hydrogen only. Okay, if you recollect. Okay, the major product, even instead of Br there was a hydrogen, so it doesn't make a difference. But now since Br is different than two hydrogens, so it makes a difference. So we'll get conformational isomers. Okay, that's the logic. Very simple. Conformational means in the space, okay, because the rotation we get a different configuration. Right now this Br is here, but there is a possibility that it can be here also. Okay, in place of this because of the rotation. Please remember this is the tetrahedrally arranged. Okay, this is not in the plane. Carbon being a sp3 hybridized, okay, all three groups, okay, they are basically tetrahedrally arranged. So there is a free rotation, okay, along the axis, and it leads to the conformational isomers. Okay, 6E. The minor product C6H5, CH2, CH2Br can be directly converted into intermediate compound X, which can then be directly converted into the acid. Okay, C6H5CH2COOH. Okay. So the question is being asked, identify the X. So let's try to do it. Simple. CHHHBr. So what we'll do now, please understand that if we have to get directly the carboxylic acid, it simply means that it can be obtained, okay, carboxylic acid can be obtained by oxidation, and oxidation means the source has, we need to start, okay, from alcohol, okay, and alcohol direct conversion is possible, okay, of this halogenoalkane, okay, this is the halogeno or arene halogenoalkane. So we can call this as haloalkane or halogenoalkane. Simple. Okay. So if we do the hydrolysis using NaOH, what we'll get is basically a substitution. So what we will get is just the substitution. HCHH, and this will get substituted, and once we get this, this can be oxidized, okay, using K2Cr2O7 or KMNO4 oxidizing agent, okay, and application of heat, it will get converted into basically the aldehyde, and then from aldehyde it will get converted into the carboxylic acid. So the real thing is that X is nothing but our alcohol. Okay, simple. So what we need to remember that alcohols can be directly oxidized, okay, to carboxylic acid, obviously passing through the aldehydes. So that is that logic. And basically halogenoalkanes can be converted directly into the alcohols. So that's the technique. Very, very simple. Hope you have enjoyed this. Okay. And if you are interested in having understanding similar, deeper understanding topics, okay, please do visit, okay, our website where we have uploaded the courses for chemistry, physics, maths, etc. So please do visit, subscribe so that you will have an interesting kind of understanding, okay. And besides that, Lead-IB Academy, we do provide the online coaching, okay. So again, that will help you a lot. Thanks.